The next step is cleavage of fructose 1,6-bisphosphate. The cleavage of fructose 1,6-bisphosphate is catalyzed by the enzyme aldolase. The reaction is reversible cleavage of fructose 1,6-bisphosphate. There is formation of dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. Fructose 1,6-bisphosphate is kind of cleaved in the midpoint to form dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. Now in this reaction, fructose 1,6-phosphate is shown to split into glyceraldehyde 3-phosphate and dihydroxyacetone phosphate in the presence of enzyme aldolase. We'll come to this reaction in the subsequent step. Now we can see the phosphate group which is present in glyceraldehyde 3-phosphate is the same phosphate group present in the 6th carbon while glucose was phosphorylated, and the phosphate group present in dihydroxyacetone phosphate is the same phosphate group present in the 1st carbon while fructose 6-phosphate was phosphorylated. Now we can visualize this fructose 1,6-bisphosphate to be split with the evolution of one carbonyl carbon over here and this carbon, whereas the carbonyl carbon which was already present as fructose 6-phosphate and fructose 1,6-bisphosphate is this carbonyl carbon. The next step is isomerization of dihydroxyacetone phosphate. Isomerization of dihydroxyacetone phosphate is catalyzed by the enzyme triose phosphate isomerase. The split products of fructose 1,6-bisphosphate are dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. So these are interconvertible, that is dihydroxyacetone phosphate can be reversibly converted to glyceraldehyde 3-phosphate. Now for the reactions to follow a pathway towards the subsequent steps of glycolysis, there needs to be the formation of glyceraldehyde 3-phosphate. So as a result, dihydroxyacetone phosphate is also converted to glyceraldehyde 3-phosphate, and there is the net production of 2 molecules of glyceraldehyde 3-phosphate, one molecule coming as the split product of fructose 1,6-bisphosphate, whereas the another molecule of glyceraldehyde 3-phosphate coming from the isomerization of dihydroxyacetone phosphate. Now from this reaction onwards, 2 molecules of glyceraldehyde 3-phosphate are going to enter into the subsequent steps of glycolysis, and whatever the products will be formed will be double the number of products for each reaction of glyceraldehyde 3-phosphate and subsequent steps of glycolysis. So this reaction shows the interconversion between glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, and since glycolysis needs the subsequent steps from glyceraldehyde 3-phosphate onwards, so dihydroxyacetone phosphate is converted to glyceraldehyde 3-phosphate, and essentially we get 2 molecules of glyceraldehyde 3-phosphate, one from fructose 1,6-bisphosphate and another from conversion from dihydroxyacetone phosphate. Next step is oxidation of glyceraldehyde 3-phosphate. Oxidation of glyceraldehyde 3-phosphate is catalyzed by the enzyme glyceraldehyde 3-phosphate dehydrogenase. There is production of 1 molecule of NADH as well. The reaction is conversion of glyceraldehyde 3-phosphate or oxidation of glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate. So it can be discussed as 2 steps. First is oxidation of the aldehyde group of glyceraldehyde 3-phosphate to the carboxylic acid group of 1,3-bisphosphoglycerate. In fact, 1,3-bisphosphoglycerate is still not formed. First is oxidation of the aldehyde group to the carboxylic acid group, and subsequently there is attachment of an inorganic phosphate to the carboxylic acid group, which is in fact a high energy phosphate. So first there is an oxidation of aldehyde to carboxylic acid group, which is followed by attachment of the inorganic phosphate to the carboxylic acid group. So this diagram shows the reaction wherein glyceraldehyde 3-phosphate is oxidized to 1,3-bisphosphoglycerate. First, this glyceraldehyde 3-phosphate, the aldehyde group is oxidized to carboxylic acid group, and which is followed by the addition of inorganic phosphate to the carboxylic acid group to form 1,3-bisphosphoglycerate. So this oxidation of glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate is accompanied by the reduction of this NAD plus to NADH, which is a reduced coenzyme form. And inorganic phosphate comes from the pool of inorganic phosphates in the cytosol. Unlike the previous steps, this inorganic phosphate does not come from ATP. It comes from the pool of inorganic phosphates in the cytosol. So the enzyme which catalyzes this reaction is glyceraldehyde 3-phosphate dehydrogenase. The enzyme once again is glyceraldehyde 3-phosphate dehydrogenase. Important features are generation of NADH. Now, as a result of this step, high energy phosphate group is formed, which drives the synthesis of ATP in the next step by a process known as substrate level phosphorylation. The phosphate group, inorganic phosphate group, which comes from the cytosolic pool and gets attached to the glyceraldehyde 3-phosphate to form 1,3-bisphosphoglycerate. This inorganic phosphate forms the high energy phosphate group in the product molecule, that is 1,3-bisphosphoglycerate, and the high energy phosphate group in 1,3-bisphosphoglycerate is sufficient to drive the synthesis of ATP in the next step by a process known as substrate level phosphorylation. So the next step, that is substrate level phosphorylation step, is the synthesis of 3-phosphoglycerate from 1,3-bisphosphoglycerate. It is catalyzed by the enzyme phosphoglycerate kinase. So the kinase means the synthesis of ATP from ADP, or ADP is phosphorylated to form ATP. The reaction is substrate level phosphorylation and is reversible. In this step, high energy phosphate or 1,3-bisphosphoglycerate is used to synthesize ATP from ADP with the generation of 3-phosphoglycerate. So 1,3-bisphosphoglycerate having 2 phosphate group, one in the third position and another in the first position. So this phosphate group makes this whole compound a high energy compound, and when this is converted to 3-phosphoglycerate, sufficient energy is generated, and that energy along with the phosphate group present in this compound is utilized to phosphorylate ADP to form ATP, and the enzyme that catalyzes this reaction is phosphoglycerate kinase. The next step is isomerization of 3-phosphoglycerate. The 3-phosphoglycerate isomerization takes place in the presence of enzyme phosphoglycerate mutase. The reaction is a reversible shift of phosphate group from carbon number 3 of 3-phosphoglycerate to carbon number 2 to form 2-phosphoglycerate. In this reaction, 3-phosphoglycerate, which has got phosphate group in the third carbon, is shifted to the phosphate group is shifted to the second carbon in the presence of enzyme phosphoglycerate mutase to form 2-phosphoglycerate, which has got phosphate group obviously in the second carbon. Next step is dehydration of 2-phosphoglycerate. Dehydration of 2-phosphoglycerate is catalyzed by the enzyme enolase. The reaction is reversible formation of phosphoenol pyruvate from 2-phosphoglycerate. So when phosphoenol pyruvate is formed, there is a redistribution of energy within the 2-phosphoglycerate molecule as a result of dehydration. Phosphoenol pyruvate has a high energy enol phosphate. This high energy enol phosphate group of phosphoenol pyruvate drives the synthesis of ATP in the next step, again by substrate level phosphorylation. Now 2-phosphoglycerate is dehydrated reversibly to form phosphoenol pyruvate in the presence of enolase, and the phosphoenol pyruvate has got the high energy phosphoenol group. This phosphoenol group is sufficient to drive the synthesis of ATP from ADP in the subsequent step by the process known as substrate level phosphorylation. And the final step of glycolysis is the formation of pyruvate. Formation of pyruvate is catalyzed by the enzyme pyruvate kinase. There is again the formation of ATP by substrate level phosphorylation, and it is an irreversible substrate level phosphorylation. The high energy enol phosphate of phosphoenol pyruvate drives the synthesis of ATP from ADP along with the generation of pyruvate, which is the end product of glycolysis. In this reaction, phosphoenol pyruvate, the phosphoenol group has got sufficiently large energy to drive the synthesis of ATP from ADP. The phosphate group dominated by this compound itself. So ATP is formed and the final product is now pyruvate, the enzyme being pyruvate kinase.